Welcome to the E-PG Pathashala series. This is on the subject computer science and we are talking about the paper called machine learning. And in this particular module, we are going to talk about a decision tree algorithm called ID3. It is a very famous algorithm of decision tree and we are going to talk about that. In the last module, we spoke a lot about what is the decision tree. Here we are going to see how to efficiently build the decision tree. So, this is the development team which was responsible for creating this module, and this are the learning objectives of the module. So, to explain the greedy algorithm for decision tree induction. What is the greedy algorithm? Greedy algorithm is you try to with the local available data you make the best decision, you do not wait for long term, that is what why it is called greedy algorithm in just the concept of greedy algorithm. And then we outline the ID3 heuristic for choosing the attributes. I will tell you why you need to choose these attributes, and then we will explain the concepts of entropy, impurity and information gain, which is the basis of this heuristic, and then we illustrate with an example the building of the decision tree using ID3. So, this is basically what we are going to do in this particular module. The key attributes are attribute selection, entropy, impurity and information gain. Okay. So, let us start with the basics. So, a decision tree, as we already know in the last module we described, just to reiterate that a decision tree is where each branching node represents a choice between two or more alternatives, with every branching node being a part of the path from the root to the leaf node. And the decision nodes specify a test of some attribute. As we already told you, each of the attributes has to have some measurable values, and based on that a decision node will specify a test. And the leaf node indicates the final classification of a example, a new example or a old example or training data example. So, the algorithms, there are many algorithms for decision tree. So, let us look at the algorithms. So, the basic idea behind any decision tree algorithm is as follows. So, what is this algorithm basically about? So, you have to choose, this is the basic concept of decision tree algorithms, you have to choose the best attribute to split the remaining instances and make that attribute a decision node. Now, what we are trying to tell here is, as we saw in the last module, if you take a experience table, you could have chosen any of the attributes as the root node. Now, the decision tree algorithm, up to now we just build the decision tree, right. This algorithm will try to choose the best attribute that you have to use to do the splitting, so that the remaining instances will be also classified faster, make that attribute a decision node, so that you can partition the examples appropriately. Now, what is the meaning of the best? I will come to that later, and you have to repeat this process. So, after you choose one best attribute, you will have two subtrees or three subtrees, and each of those subtrees, if there is a you have to choose which attribute to test there. So, this is what we say, repeat this process recursively for each child of that particular root node. Now, what is the stopping criteria? The stopping criteria is whole group of instances, you have to, all the instances have the same target attribute value. Okay. There are no more attributes, either there is that or that there are no more attributes, or there are no more instances that you have to consider. So, one of these three will result in the stopping criteria. So, the basic algorithm before we start off is what is called a greedy algorithm. I already defined what is the meaning of greedy. You make a decision based on local parameters or whatever is locally available without going into the complete analysis. So, this is for decision tree induction. Tree is constructed in a top down recursive divide and conquer manner. We have seen this divide and conquer. What we basically do is you divide the tree into two, and with the rest, so the examples are now split into two partitions, and the smaller partition is easier to conquer. So, that is the divide and conquer technique which we saw in analysis of algorithms, if you remember. At the start, all the training samples are at the root of the tree. So, if you have, as I told you, 20, 30, whatever it is, the whole thing, it starts with the complete sample space as being a single partition, in other words. Then the attributes are categorical, either you have it could be true or false, or it could have 3 or 4 values, and the examples are partitioned recursively based on those selected attributes. So, the selection of the attributes decides on how the partition occurs. So, you start with the complete partition, you divide it into 2 or 3, and then that you divide further and so on. Test attributes, now this is the important part. The test attributes are selected on the basis of the heuristic or statistical measure. So, how do you select the attributes? what is the meaning of select the attributes? What should be the root node? What should be the what is the attribute that should be the root node? What should be the next attribute you want to test in this branch? What is the next attribute you want to test on the next branch, and so on. So, it is a recursive procedure obviously. So, these test attributes are selected on the basis of a heuristic, on a statistical measure. It is not exactly that it will give you the best, but it is a heuristic that we are using, but we are using it based on a or it could be based on a statistical measure, which we normally they use, the statistical measure they normally use is what is called as information gain. Okay. So, this is a decision tree. We have taken a training data set. You have attributes called age, income, student, credit rating, and buys a computer. I mean that there is no special thing that you should write buys the computer, the target attribute at the end, but this is the standard that is followed. So, how many attributes do you have here? You have 4 attributes: age, income, student, and credit rating. So, the ages he has divided. Now, this division also is the design of the decision. So, you have lesser than or equal to 30, between 30 to 40, and greater than 40. So, those are the 3 ways in which the attributes, the age values have been split into 3. And then income we have split into 3 again: high, medium, low. How you define that, you have to, it depends on how you design the problem. And then student is only Boolean values, yes or no. Credit rating is again only Boolean, though it is called not yes or no, fair, excellent, that is it. And then we want to know whether the particular, that is depending on the age, depending on the income, depending on whether it is a student or not, depending on the credit rating, whether that particular individual buys a computer or not. So, again that is a Boolean target value, yes or no. So, for example, if you take one particular row, if the age is less than or equal to 30 and the income is high, he is not a student and the credit rating is fair, there are he will not buy a computer. That is what the example tells you. Now, if you have is between the age of 31 to 40, I am taking the 7th row, 31 to 40, his income is low, but he is a student and the credit rating is excellent, there is every chance that he will buy a computer. So, this is given by the example data, training data set. Okay. Now, if you do not have the examples, you can't build. So, now you have built a decision tree with buys computer. So, age is less than or equal to, now there are only 3 values that age can take in the test decision. So, lesser than or equal to 30, 31 to 40 and greater than 40. Then after that, if the age is 31 to 40, you do not have to do any testing. So, let us just go back to this example. If it is 31 to 40, high, no, fair, that is the 3rd row, high, no, fair, the answer is yes. Now, 31 to 40, low, yes, excellent, those are the 3 values, but yes. Then 31 to 40 again medium, no, excellent, yes. 31 to 40 high, yes, fair, the answer is yes. So, irrespective of what the values of income, student and credit rating is, if the age is between 31 to 40, he buys a computer. So, that is what is told here. If the age is 31 to 40, you do not have to do any other test, because none of the attributes is affecting the value of whether he buys a computer or not, only that his age is between 31 to 40. So, yes. If it is less than or equal to 30, then you have to check whether he is a student or not, that attribute. So, if he is not a student, there is no chance he will buy a computer. If he is yes, he will buy a computer. Now, if the age is greater than 40, now how do you know this? You have to, if you look here, if it is lesser than or equal to 30, okay. If he is not a student, he does not buy a computer. You are not looking at the other attributes. If it is lesser than 30 here, if he is not lesser than 30, if he is not a student, he is not buying a computer. You do not know whether he buys a computer, but if he is not a student, he does not buy a computer. Similarly, that is it, lesser than, if he is a student, he buys, but if he is not a student, he does not buy. So, based on this, even drawing this tree, so here you have, if he is not a student, he does not buy, if he is a student, he buys. Now, if it is the age is greater than 40, credit rating matters. If it is excellent, he will not buy. If it is fair, he may buy. So, this is the with the data, we do not know whether it is correct or not. This is from the examples that we have got. Now, comes the important part. How do you select the attribute? What is the criterion for the attribute selection? What is the meaning of attribute selection? Which is the attribute you will consider as in each case? So, what it means is not the attribute, you will decide on the attribute when you are designing the problem, that is not what we are talking about. How do you decide the attribute that should form your decision tree? So, which is the best attribute? Okay. the one which will result in the smallest tree. Now, we have come to the crux of the problem. The crux of the problem is the attribute that results in the smallest tree. What is the meaning of smallest tree? The least height, which means that when you start with a new example, you will get the classification earlier, that is the meaning. So, the one which will result in the smallest tree, if you choose the attribute in that way, that is your best attribute. So, heuristic is choose the attribute that produces the purest. Now, what is the meaning of this? Now, if I have examples, okay, and I choose the attribute and the examples are clearly divided into 2 or 3 sets, whatever the sets is. I mean if I choose an attribute, let us assume a Boolean attribute, okay, that it has a value yes or no, and if I do the testing, let us say age is greater than 40, not the previous example, any example, age is greater, and he buys a computer or not buys a computer. If age is greater than 40, he does not buy a computer. There is no question of whatever the other attributes, he does not buy a computer. If age is less than 40, he does buy a computer, whatever the other attributes is. Then this clear partition of the examples into clear 2 places is called a pure. Now, suppose I have lesser than 40, but only if he is a student he will buy, then when I say lesser than 40, I will have examples, target value examples with both no and yes. So, then I cannot say it is pure. This is the meaning of pure in conceptual terms. We will go into detail as we go along. Now, popular impurity measure. So, we have a measure to judge the impurity of this attribute, what the results in this attribute produces, and that is called information gain. So, information gain increases as the average purity of the subsets of the attribute increases. Now, when you take an attribute, what you are actually doing is you are partitioning it into subsets. Now, this subset you take and you see whether the information gain is increasing. If the information gain is increasing, then the purity of the subset will also that the attribute produces will increase. The more pure it is, the better it is for the decision tree to remain smaller. Okay. So, strategy, choose the attribute that results in the greatest information gain. So, what we have now been telling you up to this point is how do you choose the best attribute? The best attribute should result in the smallest tree. Now, it is not the one attribute. Now, how does this attribute do? The attribute actually divides your that particular partition into 2 subsets. Now, the subsets that is formed should be the purest. How do you judge the purity? By something called an information gain, and the information gain will increase as the average purity increases. So, you want the to be the purest. So, you choose the one with the more information gain. So, choose the attribute that results in the greatest information gain. Out of 4 or 5 attributes, choose the one there. So, which is the best attribute is what we are asking. Okay. Now, this is the crux of it, that is you have to choose one that results in the smallest tree and the purest nodes. So, this good measure of purity, as we have already discussed, is what is called the information gain. So, when will purity be the maximum and when it will be minimum? We did not discuss minimum, when it will be minimum, when it will be maximum is questions we have to answer. As we already saw, information gain is one such measure. The choosing of the attributes, the basic structure of creating the decision tree is the same for most decision tree algorithms, whatever the algorithm is. How you choose the attribute is the issue. So, the difference lies in how we select the attributes for the particular tree, that is where it changes. So, we will focus on one particular algorithm here. There are many algorithms which is called as ID3. This particular algorithm, now what is this algorithm for? The algorithm is for choosing the attributes of the tree. Which is the first attribute to test, which is the second attribute to test in this side of the tree, that side of it. This is what we are trying to do. So, we will focus on this ID3 algorithm. This ID3 algorithm was developed by Ross Quillen in the year 1975. It is actually the full format of it is iterative dichotomizer 3, and it is an algorithm invented by Ross Quillen, very famous algorithm used to generate a decision tree from a data set using Shannon entropy. So, his algorithm, the ID3, uses what is called Shannon's entropy. This Shannon's entropy is a statistical measure. So, what we do, this is the example we saw in the previous module, and what we want to do is how did we know to split on leave and then on to stall and not weather. So, there was weather also there, how did and accident and not weather. So, this is the issue that we are trying to solve. Please note, we do not have less examples. If that is, we can do it by doing some analysis in our mind, but we want to do this automatically. So, how do we do this? It is a top down recursive divide and conquer technique fashion. The first attribute is selected as a root node and a branch is created for each possible attribute value. So, if it has 3 values, 3 branches are created. Then the instances are split into subsets, one for each branch extending from that particular node, and the procedure is repeated recursively for each branch using only instances that are there in that particular branch. So, what he is trying to say is, you start with one node and depending on the attribute values you have as many branches, and for each branch you have now a new subset. That subset is again recursively you do the procedure. The process stops if all instances have the same class. Now, this is the ID3 heuristic. Now, we are coming to the algorithm. Remember, the ID3 heuristic is to choose the best attribute at each level. So, determine the best attribute, we look at the ID3 heuristic. Now, ID3 splits attributes based on their entropy. So, the entropy, how do you define entropy? Entropy is the measure of disinformation. It employs a top down greedy search through the space of possible decision trees. Greedy because there is no backtracking, it picks the highest values first, there is no question of backtracking. If you choose the highest value first, the next may not be the best, but still we do not do any backtracking. So, that is why the ID3 is called a greedy algorithm. The select the attribute that is most useful for classifying examples, that is the attribute that has the highest information gain. So, ID3 employs a top down induction of the decision tree and it uses a greedy algorithm. Its attribute selection is the fundamental step to construct, and the ID3 helps you to select the attribute to become a node in the decision tree. And there are 2 terms that are associated, entropy and information gain are the 2 terms used to process this attribute selection. So, once the attribute is selected for the current node, you generate the children node and one of each possible value of that, and then partition the examples, we have already spoken about this, and then and assign subsets of the examples to each of the partitions, repeat for each child. Now, Black and White developed by Lionhead Studios and released in 2001, that is a game, used this ID3 decision tree and ID3. It used to predict a player's reaction to a certain creature's action. In this model, a greater feedback value means the creature should attack, that is some of the attributes associated with the gaming. Now, let us take look at this particular example of some attribute which has lesser than or equal to 50k and greater than 50k. Now, you split whether the balance exceeds 50k. You have values here, those pink and yellow dots are the examples. If you look here, the split is such that if you take this particular attribute greater than 50k, you do have some yellow dots coming here. But if you split whether the yellow and pink represent the target value. Okay. Now, split of whether the applicant is employed, if you do that split, you find that the split is pure. That means, on this subset everything is in the pink class, I mean the S class or whatever, this side everything is in another class. So, 2 different classes which has a pure split. You understand, this particular greater than 50k, if you see it is not as pure. So, the information gain can be measured using what is called as impurity or entropy. Informally, it measures the level of impurity in the given group of samples. So, for example, this particular one on the left hand side is impure, while the one that is on the right hand side is pure. Okay. So, this is very impure group, this is less impure group, and this is the minimum impurity group. So, you can see that when you split into a partition, those partition or subset should have examples that belong to one of the values of the target variable. Okay. So, target has yes or no, everything should belong to yes or everything should belong to no, that is the meaning of this. Now, one common way of measuring this impurity is what is called entropy. Now, what is this entropy? It is given by this particular way, where Pi is the probability of class I, and so it is given as for every class that you have it is a summation of the minus of the probability of class I log of the probability of class I, and it is computed as a proportion of class I in that set. Entropy comes from information theory. The higher the entropy, the more the information content. So, what does this mean for learning from examples? We have taken a mathematical term very nicely and explained that this is entropy. What does this mean for learning from examples, which is the basis of our decision tree? So, here we have entropy is minimized when all values of the target attribute are the same, that means it is the most purest. If we know that commute time will always be short, then entropy is equal to 0. So, what it means is entropy is minimum when purity is the maximum. So, entropy is maximized when there is an equal chance of all values of the target value. So, suppose I have a partition in which half, suppose I have 50 samples subset, 50 is the subset, then if half belong to one value and the other half belongs to the target attribute other value, then that is the most impure. If commute time is equal to short in 3 instances, medium in 3 instances and long in 3 instances, entropy is maximized, that is equally divided. Entropy H of S is a measure of the amount of uncertainty in the set S. So, if you have only one value, there is no uncertainty. So, entropy value is 0. Entropy measures the impurity of the arbitrary collection. So, entropy will be maximum when impurity is the maximum. So, H of S is defined as for all values of x, p of x log of p of x. That means, the more uniform, more information we can gain, more entropy, more information we can gain. So, that is the idea. So, for a collection S having positive and negative samples, entropy is defined as minus, we have taken those values itself, where plus is the proportion of positive samples and p minus the proportion of negative samples. So, you take both. So, entropy of S equal to 0 if everything belongs to the same class, and equal to 1 when all members are split equally. So, if you have a set S, positive and negative, that is what we are saying. So, now let us redefine entropy as p of positive log to p of positive minus p of negative log to p of negative. So, this will give you the entropy value for a sample set. If you have 3, you will have to do it in 3. So, this is a 2 class case. What is the entropy of a group in which all examples belong to the same class? So, entropy is equal to 1 log 1, that is equal to 0. It is not a good training set for minimum impurity, it does not give you any information. Now, what is the entropy of a group with 50% in either class? Then entropy is equal to minus 5 log 2 of 5 minus 5. It is a good training set, because it gives you enough information for training. So, this is the maximum impurity. Now, let us look at information gain. So, what did we start off with? We started with entropy. Now, how do you define information gain in terms of entropy? We want to determine what is the major idea we started off. We want to determine which attribute in a given set of training feature vectors is most useful for discriminating between the classes to be learned. So, information gain tells us how important a given attribute of the feature vector is. We will use it to decide the ordering of the attribute. So, what we are doing here is we try to find out which attribute is the most useful for discriminating, and then information will give you which attribute you need to use, and we will use it to decide the order in which the attributes will be tested. So, the information gain is the measure of the difference in entropy from before and after the split on the attribute. Now, we are coming directly into our problem. So, here you have information gain as H of S minus one particular term. Let us see what that means. So, H of S is the entropy of the sample, T is the subset created from splitting S by the attribute A, such that S you have S being split into T subsets, and P of T is the proportion of and the number of elements in set S in proportion of number of elements in the target subset to the whole set, and H of T is the entropy of that particular subset. So, what we are trying to do is we are taking an attribute and we are dividing into subsets. So, what we are trying to do is we are trying to first find the entropy of the sample, and we are dividing into T subsets, and for each of the subsets we are trying to find out what is the proportion of this. So, suppose I have 10 as the original is dividing into, let us say 5, 3, 2, then 5 by 10 proportion and the entropy of the new subset. Okay, so, 5. So, that is what we are trying to find out. Now, let us see how to calculate this information gain. So, let us assume the entire population consists of 30 instances. So, entropy of parent is the average entropy of the children. So, parent entropy here is, now you have two sets there, if you can see, you have 14 samples of positive and 16 samples of negative, whichever way you take, yellow and pink. So, how do you calculate the parent entropy? Parent entropy is nothing but minus of 14 by 30. 14 is the number of samples and 30 is the total number, and the log of that. Similarly, for the other one. So, we get the parent entropy because of the two sets we have. So, actually positive and negative is 0.996. This is the way we calculate the entropy. Measures the expected reduction in entropy. The higher the value of information gain, more is the expected reduction in entropy. So, you have gain, this is the information gain, S of A is equal to the entropy of S minus the set, how you divide it to sets, where values of A is the set of all possible values for the attribute A. So, suppose it has Boolean only yes and no, you have 2. If you have more than 2, that is for example, a leave at the example we took, you have 10 am, 9 am, 8 am. So, 3. So, values and yes is the subset of yes for each of the attribute values. So, here you have the entropy of the whole set and here you have the entropy of the subsets. Okay. This is the number of samples in that subset divided by the total number of samples. So, this is how information gain for a particular sample for the attribute A is calculated. Now, we will take an example and explain this in detail. So, let us start with sample training data to determine whether an animal lays eggs. This is what we are going to take as an example. So, here is the attributes and here is the decision attribute. So, you have animal, warm blooded, feathers, fur and swims. These are the 5 attributes you have and we want to know whether particular animal lays eggs or not. So, you have Boolean yes or no and the animal can be ostrich and so on, warm blooded yes or no, feathers no, what is that yes or no, and fur yes or no, and swims yes or no. So, you have most Boolean attributes. Now, first we have to calculate the entropy of the complete set. How do you do that? This is calculated by looking at the positive and negative values. So, here you have this is the target value is only one you will consider for this. You have to first find out how many yes is there and how many no is there. In this particular example of 6 examples, we have 4 yes and 1 no. So, using that you calculate the entropy. This is 4 by 6 and 2 by 6, 4 by 6 log of 4 by 6, 2 by 6 log of 2 by 6 minus of course, and you will get the value of 91829. So, this is the entropy of the complete set of records. Remember this entropy information gain, everything is calculated in terms of the set. So, we start off with the complete set of 6 records. In this example, simple example, we have taken only 6. Now, if you take warm blooded for that particular thing, you have 5 yeses and 1 no. So, here the entropy is we just have the values, you calculate the entropy for the decision attribute only. So, here you have 5 S's and 1 no, for feathers you have 3 S's and 3 no's, for fur you have 3 S's and 1 S and that, and for swims you have 2 S's and 4 no's. Okay. So, now what we have to do is, what we are bothered about is which attribute to select. Now, in the same example that we saw the entropy of the complete set. Now, we want to know how to divide it such that we have the best gain. So, what we do by this is, we have to find out the information gain for all the 4 attributes which you use. So, warm blooded, feather, fur and swims. So, that is what we are going to do. So, how do we do this? You first take warm blooded and you take, this is the target attribute. Now, if you look here for the attribute warm blooded, okay, values of warm blooded yes or no are, you have yes or no and you have the yes as 4 yeses and 2 no's. Okay. And if you take, now what we do, this warm blooded can have yes or no. So, yes you have 5. So, the yes of yes is, that is the subset is 3 yeses and 2 no's for all the yes values that we have shown here. And so, the entropy for this is 0.97095 using the entropy measure, and for no it is only, there is only one no and that no is yes. So, it is equal to 0 because all members belong to the same class. For an entropy, remember, if all members belong to the same class, value is 0. So, you have 0. So, now you have to find the information gain. Information gain is the entropy of the whole set that you are using for division minus this 5 by 6 of 0.9705 which you have calculated here plus 1 by 6 of 0. So, you get the value as this. So, this is the information gain if you take the original set of 6 records and split it, first attribute you use for splitting is warm blooded. So, this is one value. Now, you have to do this for each of the 4 attributes, warm blooded, feathers, fur and swims. So, now let us take the next one, which is feathers. Now, if you take feathers, you will see that the lace eggs, the entropy value is the same that we calculated for the entire set. Now, you take feathers. Now, feathers has 3 S values and 3 no values. So, for the attribute feathers, the value of feathers is S and no, and that is the value you have, and you have S has this S has 4 S's and 2 N's, this we saw before. Now, if you split it according to feathers for S, how many S's do you have? Yes. In that S, you have 3 S's, no no's. So, the entropy is 0, as we told you, if it belongs to the same attribute value, I mean everything has the same, the entropy is 0. For no you have 3 no's, and in that you have 1 yes and 2 no's. So, it is 1 and 2. So, the entropy of this you have to calculate with the positive and negative values that we did before is 91829. And this gain, if you split using feathers, because you use that attribute, is the obtained for lace eggs earlier minus what you obtain from here. So, what you get is this is the positive negative which we did, one was 0 value. So, with that you get one is 0 value. So, you get the information gain because you use feathers is 0.45914. Now, this you have done for 2, warm blooded and feathers. Now, you have to do for the others, right. So, now you take fur. Now, in fur what happens? The attribute lace egg is, and yes or no is again the value. So, and S as we already know is 4 S and 2 no's, and now if you choose fur as the attribute, you have 0 for yes, you have yes. So, there is only one yes and the value is no. So, entropy is 0, and for no you have 5 values and which all 4 yes and 1 no. So, that is what you have here, and you find the entropy value is 0.7, the same way we calculate positive minus negative, and the gain, because you use fur as the attribute, is the original one for the complete sample minus the entropy of this, which is equal to 0.317. So, the information gain if you choose fur as the attribute is this. Now, again you have to do for swims. So, swims again S and no value, S is the same. So, S is 1 yes, 1 no. Here again the entropy value is 1 because there is equal division, equal members, and for no you have 4 values, of which 3 are S's and 1 is no. So, you get the entropy value as 0.81127, and with this you calculate the the gain as the entropy of the complete set plus the for the true attribute values. So, with that you get the value as 04411. So, we got these 4 values. Okay. So, the maximum value you get is when you split using feathers. This is an automatic method, please note, we have not done anything, that is we have just taken S and no values, here it was S and no, simple. So, what we got is the maximum information gain is for feathers. So, which means this is the attribute you have to choose as the root node. So, we started with a complete set of 6 and we chose feathers. Now, what happens after you choose that? So, you choose feathers. So, now feathers yes, then you have that it lays eggs, there is no need of another attribute check. Now, if it is no, then you have to check. So, now we have to find out. So, we have chosen the first attribute of the root of the tree as feathers based on the maximum information gain, which we found by considering the values corresponding to the decision attribute. Now, the S we do not have to consider, we have to consider only the nose of feather. So, this it reduces to 3 records. Now, we have to do what? This we do not consider, we consider warm blooded, fur and this, and see which we should use. So, we have to repeat the procedure for crocodile, dolphin and koala, okay, which gives me 1 yes and 2 no's. So, for this set, now the set that I am considering is not 6, the set I am considering is only 3. For this set I have to find the entropy. Okay. So, that value is which I take is positive value, negative value, I get 9186. Now, with that 3 values alone I have to do for warm blooded. When I do for warm blooded, like just like before, the entropy here is 0 because for S there is only one value, both I get as no because both belong to the same class. So, here obtained for lazy eggs is 0.9187, this value gives low. So, I get 91829. The same thing I can do for fur. If I do for fur, similarly I get 0.25162, and for swimming I get the value as 0.25162. I have not explained it, it is very clear when you look at that. So, the same way we are doing this, and then what happens with warm blooded I get the maximum value. So, the next attribute of my tree has to be warm blooded. If I get warm blooded, this is all, I do not have to check the other attributes at all. This is the final decision tree. I have done only 2 tests, okay, though we had 4 attributes. How did I do this? I found out the entropy of the thing and try to find the information gain when I use each and every attribute for the splitting. So, this is what we did, and this is the ID3 algorithm that we use. So, you can try this example with factors affecting sunburn. Here the slight differences, instead of only yes and no, you have other values also. You can try this out. So, the summary of what we covered in this particular module is we explained the greedy algorithm for decision tree induction. We outlined the ID3 heuristic, which is used for choosing an attribute. Remember what we did, we found the entropy and we found the information gain. Then we explained the concepts of entropy, impurity, information gain, and we used a complete example to illustrate the building of a decision tree using the ID3 heuristic. So, thank you.